Hello guys, welcome to our first AP Chemistry review video. Today we'll be going over Unit 1, which is Atomic Structures and Properties. We will split Unit 1 into two videos. The first one will be from Units 1.1 to 1.4, and the second will be for the rest. So let's go straight into it. Topic 1.1 is moles and molar mass. So you should be pretty familiar with this topic already because the whole AP Chem curriculum revolves around this. However, if you want to review quickly, we can talk about how we can relate moles and atoms. So we can relate moles and atoms to the conversion factor, Avogadro's number over moles. So, and Avogadro's number, that just equals to 6.022 times 10 to the 23rd amount of something. So you can have an Avogadro's number amount of jelly beans, which is a lot. However, you can also have an Avogadro's number of electrons, which won't be as much, um, not as overwhelming as jelly beans. So we cannot count particles directly here. So we identify a connection, which is the conversion factor between the masses of the substances and the number of participating particles. One part I want to talk about is the atomic mass unit, AMU, and that's the unit to assess the mass of an individual atom. So if a question asks you, which I highly doubt, but if it asks you, what's the mass of one atom of oxygen? Then you go to your periodic table and then look up where oxygen is, and you'll see that it's 16.00 AMU. Though if the question or problem asked you to give you the mass of 1 mole of oxygen, then that would be 16 grams. Just wanted to clarify that. So remember, atom, AMU, mole, grams. There's lots of practice problems you could have based on already these three concepts. However, that'll be for a separate video, or we'll send out a link for resources in the Discord, which will be put in the bio for this video later. So moving on to topic 1.2, that's mass spectroscopy of elements. So before we go into what the hell spectroscopy is, let's talk about what elements are. So each element, which is the letters, the two letters on the periodic table for each little box, each element consists of a certain type of atom that is different from the atoms of any other element. So no two elements can have the same properties. And though if you look at the groups, which is the columns, they have similar properties, but an element is unique because it's an atom that has a number of protons that no other element has. The amount is not the same between two elements of protons. So an atom is the smallest unit of matter that still retains properties of an element. So remember, atom still retains properties of the element, and it is the smallest possible thing that can resemble those characteristics of the element. And an atom can still be broken up into smaller particles, but these aren't as unique. So of course, there's the neutron, the proton, and the electron. So the neutron and proton have basically the same mass. So we can both say that neutron and proton have a mass of 1 AMU. And an electron, well, it still has a mass. It's just that the mass is so small, you just like to say it's negligible for our own convenience. So we can just say that an electron has 0 AMU. And Self-explanatory. A neutral, has no charge. Proton has a +1 charge because of pro, and the electron is just -1 charge. Um, and if you really want to see how the mass of an electron compares to the mass of a neutron and proton, an electron has a mass that's 1/2000 of what a proton and neutron have. So let's go into some basic notation. People like to call this like the isotopic notation. You see this in nuclear chemistry a lot, but that's not covered in AP Chem. So the number on the top, that's the mass number. And the number on the bottom, that's the atomic number. And the mass number is just the number of protons plus the number of neutrons. And you can manipulate this equation to get the number of neutrons, which is the mass number, minus the number of protons. Minus the number of protons. And this equation is derived just because, again, electrons have no mass, so the only mass that is found in that atom is through the nucleus, which is just the number of protons and number of neutrons. Because again, it's just one AMU for both. And the number on the bottom, that's the atomic number. I already have it over here. Whoops. And that's just the number of protons. And like I said, kind of roughly before, sorry for that, no two elements can have the same number of protons. If somehow a sodium atom loses a proton, then it becomes a new element. So it'll go down. And that's only possible when there's a nuclear reaction, like a decay reaction, but you don't need to go into that for the sake of AP Chem. Um, and yeah, the atoms of the various elements differ in their number of subatomic particles, but all atoms of a particular element have the same number of protons in their nuclei. And again, for neutral atoms, which may not be the case in most problems in AP Chem, um, electrons equals protons, the count of them. If they don't, then it gets charged. So moving on to isotopes, because we just talked about that. All atoms of a given element have the same number of protons, but some atoms have more neutrons than other atoms of the same element and therefore have greater mass. So what that's just saying is that some elements, say for example, sodium, some may have like more neutrons, so might be 25 or 24 or maybe even smaller, 22. And what all these different what all these different masses are saying is that there's isotopes of sodium that have less neutrons than this 23 sodium, and some that have more than that. And if we see the periodic table, the mass number on there is just the relative weight, which is just multiplying the abundance of that specific isotope in nature times how heavy it is, and then sum all of those numbers up. So a common question could be there's a graph like this, and the y-axis is the percent abundance or the relative abundance of that isotope in nature, and the x-axis is the AMU, which is just the mass of a particular isotope in nature. So a graph could look like this. And obviously this column or this particular isotope is most abundant in nature. And those mass numbers on the periodic table with the little decimals next to it, that's because um, why there's decimals there is because you end up having to multiply this percent abundance by each mass of isotope. and then sum all of these up to get the weight. And so a way scientists can do this is through through a technique, mass spectrometry. And it's just that the mass spectrum of a sample containing a single element can be used to determine the identity of the isotopes of that element and the relative abundance of each isotope in nature. So the equipment kind of looks like this for it, a spectrometer. So you enter the sample of your desired element here. There's a vaporizer over here, and then it goes through a tube, and now it's ionized. So ionized, they're all ions are charged, and then they go through an electric field or a magnet over here, and there's a detector on the end of it. And so the lighter ions, which are the lighter isotopes, get deflected further. There's a bigger arc over here. However, the heavier ions, they don't like to get deflected because they're strong. So they just go straight to the detector. So the average atomic mass of an element can be estimated from the weighted average of the isotopic masses using the mass of each isotope and its relative abundance, like I said with the graph over here. And the mass of various isotopes of an element can be determined by a technique called mass spectrometry, which is through this. And the most abundant isotope of let's say, I don't know, selenium has a mass of 80, but there are four other naturally occurring isotopes of selenium, which is the case for almost every element on the periodic table. There's always going to be other isotopes with other mass numbers. And like I said, the number of the mass on the periodic table with the little decimals on it, that's the average atomic mass, which is the weighted average of all five isotopes of selenium shown in like a spectra. And the molar mass of an element will give you a pretty good idea of the most common isotope of the elements. So a way the AP can ask this kind of graph question is they'll give you a graph already and they'll ask you what element it is. So you just eyeball and draw little lines like that to the top peak of the histograms bars and then just add them all up and find what element that is. We're halfway there. We'll go over what topic 1.3 is now, which is the elemental composition of pure substances. This is a really quick topic. All we need to know is that a compound is equal to the individual molecules or formula unit. And we can add on to this with the law of definite proportions. And that's just saying, let's have an example for this one. So you have CaH6O4, some organic molecule, and then you have C4H3O2. So what's going on here is that the formula, even on the bottom, that's going to be called the empirical formula. Empirical. And the one on the top, that's called the molecular. And so the law of the definite proportion says that the ratio of the mass of the constituent elements in any pure sample of that compound is always the same. So that's saying that the ratio of the empirical will always equal to the ratio of the molecular of the same kind of formula unit. And the empirical is just the lowest whole number ratio of atoms, the elements in the compound. And you can check for it yourself. 8 divided by 2, that's 4. 6 divided by 2, that's 3. 4 divided by 2, that's 2. So it's the same. Now, we'll go on to our last topic for this video, the composition of a mixture. So what is a mixture? So a mixture contains molecules or formula units of two or more types in various proportions. And an elemental analysis can be used to determine the relative numbers of atoms in a substance and determine its purity. So you all probably did this in the labs already, but let's just go over two basic terminologies. This is what you call a homogeneous mixture. sorry, homogeneous. Sorry, my pronunciation is bad. And a heterogeneous will look something like this. So a homogeneous mixture looks uniform throughout. However, heterogeneous mixture, hetero, you can visibly see that it is not uniform, usually because of density differences. And a good example I remind myself is that heterogeneous, okay, that's chocolate chip cookie. You can visibly see that there's chocolate chips on the cookie that make it not look uniform. And that's basically it for this video. In the next video, we'll cover topics 1.5 to 1.8, and we'll send out a problem set for all of these topics we covered today. Thank you for joining us today, and see you in the next one.